Hi, welcome back to Father-Offspring Interviews, episode 38. We have lots to cover in today's episode, so we are getting right to it. First, Mark from England says, Parkinson's, one disease or a suite of different ones related by their connection to dopamine? Why is there such an increase in case numbers?
Okay, Mark, Parkinson's disease, one of those diseases where if you have a choice in the matter, you do not want to get it. Parkinson's, as with so many of these, people spend a lot of time debating is it one disease, is it multiple subtypes, the dread heterogeneity of symptoms. People who study this for a living study nosology, the study of categorizations. With Parkinson's, probably the most meaningful, at least for my money, is the difference between what would be called familial Parkinson's. It's due to a mutation. It runs in your family. If you have a parent who got it, you've got about a 50% chance of getting it, or sporadic Parkinson's, which is about 95, 98% of the cases. Familial, it's more vicious. It gets you in an earlier age. You fall apart faster. This is a very common sort of theme with a lot of these slow neurodegenerative diseases. Okay, so Parkinson's, it is on first pass a movement disorder. You have trouble initiating movement, akinesia, starting a movement and the inability to initiate it. You have slowed down movement, bradykinesia. You have increased tension in your muscles, so it's harder to push it down. And seemingly paradoxically, you also get a Parkinsonian tremor. That's weird. In the akinesia, that's less movement than normal. Bradykinesia, that's slower movement than normal. Rigidity, that's more resistant to yet why are you tremoring? And it turns out the totally charming explanation is we actually are all tremoring all the time. Something like our hands are tremoring at 12 oscillations a second. And just as everything else slows down with Parkinson's, the tremors slow down so that they become more visible, so that you're now seeing them at a rate of 3 or 4 per second because the intervals have more excursion there. It winds up being visible. Okay, so that's Parkinson's. Since the early 1960s, there's been ground zero in Parkinson's, a part of the brain called the substantia nigra, Latin, Greek, whatever dark substance. You slice a brain open, you don't stain it, you just look through, and there's an area with dark bands, and that's the substantia nigra. You look at the substantia nigra of someone who has died from Parkinson's, and it is just carpet bombed. 70, 80, 90% of the neurons are dead. Interesting thing. And everyone else who doesn't have Parkinson's, by the time you're 60 or 70, you've lost almost half your neurons there, and things are perfectly normal. Weird. What's that about? That tells you there's a lot of redundancy, a lot of parallel processing in the wiring of substantia nigra because you can use 50% of them. That's your remainders, and you still are in pretty good shape. Lose 60%, you got a slight Parkinsonian tremor, 70, 80%, and that's it. You officially have the disease. So that was the big bombshell of this is the part of the brain where this is going on. And what people soon figured out is it's all about this neurotransmitter dopamine. Dopamine, we know about dopamine, reward, pleasure, anticipation, goal related behavior, all of that. This is dopamine in a completely different part of the brain where what it has to do is fine motor control and initiating movement. And for people who care, substantia nigra is at the very center of what's called the extrapyramidal system. Blow it out, and the net result is it is very hard to initiate movements and move them at a normal speed, and you got the disease. Okay, so the question becomes, why are these dopamine neurons dying? And it turns out because of like a singularly bad piece of design on the part of the brain, which is when you use dopamine as a neurotransmitter, as with any neurotransmitter, after it's done its thing, it's come out of the axon terminal, floated across the synapse and bound to receptors here, and then it comes floating off. At which point you got to clean up after yourself to end your neurotransmitter signal. Two options: dopamine could be taken back up into the presynaptic neuron, or it could be broken down by an enzyme and then just flushed out. And in this part of the brain, the problem is the breaking down the dopamine, the flushing it out. Because it turns out a weird feature of dopamine is when you break it down every now and then, rather than producing something that you could basically eventually turn into water and oxygen perfectly safe, occasionally you can inadvertently generate a really bad type of oxygen radical, particular type called hydroxyl radicals. And it's because there's the normal pathway of breaking down dopamine, an intermediate hydrogen peroxide, a mild oxygen radical, and then you break it down to water and oxygen. That's great. However, if there is iron around, you can instead catalyze that intermediate form into becoming these horrible hydroxyl radicals. Iron, where's the iron coming from here? That's what's being retained in the substantia nigra. It has something called neuromelanin, which binds iron there. And as such, just going about your normal 50, 60, 70 years worth of business, your substantia nigra generates a lot of this really damaging oxygen radical, and that's why you're losing neurons throughout. That's why we have to have lots of redundancy in the system, lots of parallelism, so that you can afford to lose roughly half of them and you're still in fine shape. Okay, so the question becomes what to make of the sense that Parkinson's is becoming more common. First thing to possibly bring up is this is not interesting at all. People have gotten more attuned to it. There's somebody's more likely to be seen by a neurologist than 100 years ago. Do all sorts of the careful controls to get those confounds out of the way. And the incidence of Parkinson's is rising. And it's tending to rise at a faster rate than some of the other common neurodegenerative diseases, Alzheimer's, ALS, things of that sort. So, what's going on with that? What's happening with that? And the first hints come historically. You go back to the ancient scripts of the elder scribes, thousands of years, and you see reasonably good descriptions of dementia. You see highly accurate descriptions of an epileptic seizure in the Bible. You don't see anything about Parkinson's disease until the Industrial Revolution. Ah, interesting. Spotted by Dr. Parkinson, English neurologist, who began to note this. So, okay, so people have been noting weirdo neurological diseases before that, and this appeared to be a new one, or at least previously very rare. And then people started noting there were some clusters. Certain individuals in westernized, industrialized societies were more at risk for Parkinson's disease. People who worked in certain heavy industries, smelting of pig iron, and I have no idea what that actually is, but that's like muscular, beefy men pouring molten stuff and all sorts of vaporous stuff come. They have high rates of getting Parkinson's disease. People who apply pesticides for a living, pesticide applicators, turned out to be a cluster. Then people, it turned out, living near farmland, living in farm fields that sprayed a lot with pesticide. People whose well water in the middle of their farm country is coming from water runoff. And this turns out to be a cluster of people who are more at risk for Parkinson's. Concussive head trauma is also part of the list, but there were all these hints going on there in the field, some sort of environmental toxin, an environmental cause of some of the cases of Parkinson's, explaining the increasing incidence. So that was lurking in the background, and there were people constantly pushing for maybe we're looking at a disease where a lot of the cases are diseases of an environmental neurotoxicological nature. Then in the early 80s, there was this breakthrough, one of these made for TV movies, one of those flukes, horrendous, tragic flukes, which occurred actually fairly close to where I am. And it's in San Jose, not far from here. A number of young people showed up, people in their 20s, who appeared to have come down with Parkinson's disease. Severe, severe Parkinson's, 20, 30 years before you would ever see hints of it, progressing from the first tremors to incapacitated over the course of weeks rather than years to decades. And these people were soon dead. And look at their brains afterward, and whoa, their substantia nigra was blown out of the water. And it turned out there were a few other clusters of 20 somethings who went down with the most aggressively over the top case of Parkinson's anyone had ever seen. Sleuthing began, and it turned out all of them had taken a synthetic drug shortly before that, a type of synthetic heroin, which was all very trendy at the time. And who knows what grad student at UC Santa Cruz, grad student in chemistry, was synthesizing it. But they identified a number of pockets where these were all people who had taken synthetic heroin shortly before their first symptoms, and people going and checking the residues and figuring out in all cases the chemist had made a mistake and inadvertently generated a compound that nobody had ever studied before, a compound that came to be called MPTP. I don't even remember anymore what that stands for, but this indirectly generated the mother of all oxygen radicals, extraordinarily damaging. And people went wild. Okay, so MPTP, I guess it got into the brains of these people who were soon dead from their uber fast Parkinson's. And it was soon figured out MPTP was converted into something else. But the main thing was it was then taken up by dopamine neurons, and in particular, dopamine neurons in the substantia nigra, after which it ran wild, oxygen radical damage, oxidative damage, blow the neurons out of the water, and you've got this severe case. So everybody at the time in the field went wild, because up until then, if you wanted to study Parkinson's disease in a lab animal, what you would do is stereotaxic neurosurgery. You would go in and you would destroy the substantia nigra, which differs from the real thing in all sorts of subtle but important ways. And here was a drug that could induce Parkinsonian symptoms in the matter of days if you put. What a great research tool now for studying Parkinson's. Totally terrifying. I was in grad school at the time, and somebody in my lab, some postdoc, decided he wanted to start studying something with MPTP, and we were scared out of our wits that that stuff was in the lab. This was like the most toxic stuff anybody had ever seen, but it's an amazing research tool for studying Parkinson's. And what people began to slowly come around to was a view that this was not a research tool. This is a version of Parkinson's. This is a version of some environmental toxin made by your friendly neighborhood designer drug grad student chemist making you synthetic heroin. But this was a first drug identified that could produce something that looked like Parkinson's disease. And people then had to go back and studies with very slow exposure to MPTP in lab animals, and you saw a slow emergence of something like Parkinson's rather than over the course of a weekend. And yeah, this sure looked like it. At which point, people got really interested in the structure of MPTP, because it turns out it had a lot of similarities to a bunch of pesticides and herbicides and industrial waste products and byproducts. Two of the ones at the top of the list, something called paraquat. Paraquat is a pesticide which the US dumped thousands of tons of this stuff on poppy fields in Peru and Afghanistan back when to wipe out heroin fields. Paraquat, a closely related one, rotenone, and suddenly this pesticide connection looked very real. And since then, people have been working out the fact that in an awful lot of cases of Parkinson's, it's an environmental toxin, a neurotoxin, a byproduct of industrialized agriculture. And you find residue of paraquat inside the lungs of children of migrant farm workers who every day the parents come home sprayed with this stuff from some crop duster, and the kids wind up getting lots more in their brain than an adult would because the barrier is not as mature at that point. So at this stage, you know, there's a subset of cases of Parkinson's that are entirely due to a mutation. There's a lot others that are heavily influenced by your genetic backdrop, but all of it is within a framework of environmental toxins. Pesticides have the capacity to do that. Okay, amid that, though, before you freak out, the obvious question to become is, we're all consuming some of this stuff. Yeah, someone who sprays the stuff on a carpet as an applicator 10 hours a day kind of thing is getting a whole lot more of it. But there's some of it in the water, there's some of it in the food, pesticides from the food. Often it's this type that causes dopaminergic damage in your substantia nigra. And the obvious question becomes, not everyone who worked in a pesticide manufacturing chemical lab develop Parkinson's disease. Not everyone who is a crop duster develop it. Where do the individual differences come from? And what people are beginning to figure out is it's your genetic backdrop. How good are you or bad are you genetically at taking care of the sort of misery that one of these pesticides can cause? First off, how good is your liver breaking down pesticides? Because that's what the liver does. And does it break it down so efficiently that there's none of it left to get into your brain? Individual differences in the genetics of how good your liver is at that. Now it's heading towards your brain, the stuff that wasn't broken down. And you got this thing called the blood-brain barrier. And what you see is inside it are all sorts of pumps that could pump out stuff that should not be there, xenobiotics that can pump them out. How good are you at pumping things out? What version of the pumps do you have? How effective are they? And that explains some of it. Once you got stuff getting into the brain, how good is your brain at making antioxidants to try to mop up some of this stuff? How good is it at trying to grow sort of processes of surviving neurons to compensate for what's been damaged? And what you see at this point is profoundly horrible neurobiological luck, and you're somebody who gets Parkinson's disease, even in the absence of any sort of history of heavy exposure. But for most other people, it seems to be a combination of how much environmental exposure and what are your defenses like biologically inside you, and what's the genetic differences that explain how we differ as to how good we are at it, and put those pieces together. And that probably explains a lot about Parkinson's disease. And the fact that stuff that didn't exist 300 years ago and now is commonplace in all sorts of places where we wouldn't want it, our food, our water, so on, that helps to explain why there's the increasing evidence of Parkinson's disease. Be careful what you wish for, including the Industrial Revolution.
So our next question is from Shiyang from Taiwan, who says, is severe inequality in the world today a result of people's belief in free will? Could embracing determinism be a way to eliminate inequality?
Yes, I could stop right there, but predictably I won't. Um, Inequality is incredibly fueled by the notion that there is free will between the lines, that the world is a just place, that people earn, deserve, are entitled to things that they in fact are not. And in this realm, this is this whole domain often called system justification. Yes, it makes sense that we have a highly stratified society. It makes sense that we have haves and have-nots. It makes sense, system justification. And a belief in free will is one of the engines for a belief that your system is justifiable, is just. And it's clearly bad news if the belief that poor people are responsible for their poverty is something that's believed by the people up on top, it's, I think, a hell of a lot more corrosive if the notion that poor people are responsible for their poverty is something believed by the people who are poor themselves. And they get told that all the time.
All right, to wrap up, a number of people, Max from Austria, Elisa from Brazil, Emma from Missouri, and Gunnar from Sweden, asked about the brain basis of sexual identity. So, how do cis and trans brains differ?
Well, one could hardly pick a more inflammatory topic and oh so politically relevant in its tragic consequences as of late. Okay, cis and trans brains. The starting point for all of it is the notion that biology is highly dichotomized, is highly binary. It comes as either Coke or Pepsi, yes or no, chocolate, vanilla, whatever binary things I could come up with. And biological systems, sexual differentiation turns out to be much more of a continuum than a binary than people used to think. People used to think there's a clear lock and step sequence by which the biology, the binary biology of sexual differentiation is locked in, which generates the next binary, the next, and the next, as follows. The first starting point is the binary nature of sex chromosomes, your XX or your XY. You got two X's, you're female, XY, you're male, and that's all there is. And that then determines the binary nature of your gonads. Are they ovaries or testes? Which then determines the binary nature of what gonadal hormones you are secreting, estrogen, progesterone, or testosterone, which will then determine the binary nature of your genitals and whether you have a vagina, clitoris, male penis, scrotum, where the gonads are, and then secondary sexual, and a clear dichotomized pathway. And what the biological advances have been about is seeing that none of those steps are always clearly dichotomized, always clearly binary. Chromosomal level, you're either XX or you're XY. Turns out there's all sorts of other variations, XYY, single X, triple X, endless variations on that. They're all quite rare, but nonetheless, chromosomally, the sexes do not come in just two absolute dichotomized flavors. Next level, ditto for your gonads. There's all sorts of disorders. There's all sorts of circumstances, rare ones, where you will get somebody whose gonads are a mosaic, a chimera of a mixture of ovarian cells and testicular cells. Something called ovotesticular disorder. There's a number of related ones. So it's not always one or the other. Hormones, it's not always one or the other. Males secrete a certain degree of female typical steroid hormones. Females secrete considerable amounts of testosterone related hormones out of their adrenal glands. That's not clearly dichotomized either. Next step up at the level of the genitals, and it turns out that's not so clean either. And a remarkable finding, a substantial subset of people with great frequency are born with sexually ambiguous genitalia, where it's not quite clear if we're looking at a boy or a girl. And this is really more common than one would think. It is often corrected with reconstructive surgery, and there's a horrendous history of sort of abuses that has taken in some sort of tragic individual cases. But the main thing is that's not even cleanly dichotomized. You can have a phallus that's kind of intermediate between an engorged clitoris and a penis and a dead end vaginal opening and all sorts of stuff. Like, how common is any of this? The chromosomal exceptions to the binary are pretty rare. The gonadal are quite rare. The endocrine, there's massive overlap. The genital, one of the leaders in the field, and Fausto Sterling at Brown University, in this one very influential review in the field, estimates something like 1% to 2% of people are born with sexually ambiguous genitals. Think about that, 1 to 2%. You walk through your town square, and the person you pass is more likely statistically to have been born in some intersexual state than they are to have an IQ over 150. So what we're seeing is this lock and step. It's binary and dichotomized, and this determines that you can get dissociations at every one of these levels, which of course brings us to the brain. And people were blown away in the 70s, starting there, by the discovery that there were structural differences in the brain depending on your sex. Ooh, the sexually dimorphic brain, different shapes, different sizes, different parts. Since then, different neurotransmitter concentrations, different everything. Ooh, everyone shouted there is a male brain and a female brain. And that completely distortive false dichotomy has dominated the field ever since. Yeah, statistically, on the average, this little sub area of the hypothalamus tends to be bigger in this sex than in the other one. Whether you're looking at a lab rat or a monkey or a human or whatever, there's a whole array. There's like dozens of different sexually dimorphic regions in the brain, where on the average, there is a difference in the size and the function of the whatever. First thing that comes out of that, woo, how big are these differences? Are they big enough? Are they dramatic enough? Are they consistent enough that you could look at one sub area of the brain, the hot spot? One of these is called the bed nucleus of the striae terminalis, and look at it under a microscope and know the sex of the individual who it came from? Not a chance. These are distributions that are very heavily overlapping. You cannot sex a human by knowing the size, receptor levels, anything about a particular part of the brain. Next caveat against the enthusiasm that there is a male brain or a female brain. So you would say, okay, so at least in this part of the brain, this is an individual who's pretty strongly in the female direction, for example, in terms of its size, its shape, its smell, its flavor, whatever. And thus, presumably, it's somewhat on the female side in the 12 other parts of the brain that are statistically sexually dimorphic. And you look at it and no, that's not the case. There's a mosaicism. It's a rare person where all of the sexually dimorphic parts of their brain are dimorphic in the same direction. Instead, there's all sorts of variability with that. Okay, so that's our backdrop for now saying, whoa, so what's up with people who say this is not really what my sex is? This is not the sex I identify with. It's the other one. What's up with them? And Medicine Forever had a very clear answer, which is for some weirdo reason, given this person's chromosomes and gonads and hormones and genitals and secondary sexual characteristics and everything, for some weird reason, they think they're a different sex from what they actually are. And that ushered in the possibility to now look in the brains of cis and trans people with a very simple question. When you look at a trans brain, when you look at those sexually dimorphic regions, are they, for example, in an individual who was born male but says they have never felt male? Do their brain regions that are sexually dimorphic look more like your textbook male region or female region? And the first work of this was done by a neuroanatomist named Dick Swab in the Netherlands, who's amazingly accomplished scientist. And he first published extremely thorough studies showing basically you get somebody who chromosomally, gonadally, et cetera, is, for example, female. And they say, you know what? I don't care. My entire life I have felt male. You look at the sexually dimorphic parts of their brain, and it's closer to the male average than the female average. Or you look at someone who's male, who said, I've always felt female, same thing. And landmark study of looking at this, oh, wait a second, there's a confound. Lots of people who undergo sex changes, there's surgical stuff, there's hormonal stuff, and you're suddenly taking hormones of the stereotypical opposite sex. And is that, no, you even look at people before they transition, before they take any of the hormones. And the first reports came in showing you got someone who says, I may be female in all these ways, but I've always felt male for as long as I could remember. You look at the dimorphic parts of the brain, and they more resemble your typical male brain than your female. In the years since then, that's become sort of a cottage industry. A lot of studies that have been done since then, not just the size and structure of different brain regions, not just the neurochemical makeup, but the level of activity in this or that brain region when you're doing functional brains. There's a whole world by now of people looking at. So, what's up with people who are seemingly this sex by all of those biological criteria, but say that nonetheless they have always felt like they are the opposite? The finding has softened a little bit since Schwab's initial studies. And probably the safest thing to say at this point is if you have someone who, despite their chromosomes, etc., they're supposed to be one sex, say, I feel like the other, you look in their brain and it is not particularly like the brain of the sex that everyone would expect it to be. It is not structurally a brain that is in close agreement with the chromosomes, the gonads, et cetera, et cetera. It's not as far in the other direction as those first studies suggested, but mainly the point is if you have someone who says, I don't care what my chromosomes, gonads, etc., and so on say. I don't care if they all collectively say, I am this sex. I have never identified with that sex. I have never felt that way. You look in the brain, and the neurobiology supports this. So what does this suggest at the end? I have this like silly bias that if you got to choose between like the nature of somebody's gonads and the nature of their brain and trying to make sense of what sort of person they are, I'd listen to how the brain is voting every time. What this begins to suggest is rather than the old model, for some reason, this person who is of sex number one, for some reason, they think they're actually sex number two. What I think is much more accurate is for some reason, this person who is sex number two had incredibly bad screwy luck and got handed the body of someone with sex number one. I think that is closer to a description of what's happening, which is if at every level you can dissociate the chromosomal story from the gonadal, from the endocrine, all of that, that if you have a dissociation, everything in agreement up to the level of the brain, what the brain is saying is going to be far more worth listening to, in my view. And that's much more a picture of someone who got stuck with the wrong kind of body rather than somebody who, for some reason, isn't comfortable with the sex that they are. So that's what's up with trans and cis. That says absolutely nothing about any of the controversies that are scorching our schools and voting booths. And I'm not going near any of that with a 10-foot pole. Neurobiologically, that's what you wind up seeing. That's the current knowledge of the field.
And on that note, that is it for episode 38. So keep submitting questions at the form found in the Instagram story highlight and bio or the YouTube video description. I'm Offspring Sapolsky, and thanks for your continued support of Science and the Beard.